Hi,
Kita
thank
ra,
you,
ma'am.
Sir Baron, for your report, by the way.
Makita ra, ma'am.
Yes, sir. Makita ra, sir.
Yes. Sige, start.
Sige, sir. You may continue, sir.
Yeah, good evening, everyone. For my topic, I will be discussing about nuclear energy, which includes nuclear power plants. So, once again, I'm Dick Stephen Mahino. So, welcome. In this, we have four major topics in this one. So, first, we've got the introduction. In the introduction, I will be discussing about nuclear energy, nuclear fusion, and nuclear fission, as well as the history. For the second part is all about the operation. We will talk about nuclear power plant, nuclear fuel cycle, and the nature of load. For the third topic, we'll go through the status. So first, the global status of nuclear energies. Second, the local status, and I also included the nuclear power infrastructure development. And lastly, we'll be tackling about the future. So what's the future of nuclear energy? So in this part, I included the advantages and the disadvantages. And then what are the emerging technologies? So let's start for the introduction. So first, so what is nuclear energy? So the energy stored, then released from the nucleus of atoms produced through nuclear reactions. It's either through fusion or fission. So from the word itself, nuclear, it actually comes from the nucleus of atoms. And I guess we are very familiar what is nucleus. So actually, in order to get nuclear energy from the nucleus, we need nuclear reactions, and the very popular is the nuclear reactions or the fusion and the fission. So as for the fission, first let's go for the nuclear fission. So it is the process by which two light atomic nuclei combine to form a single heavier one, which takes place in the state of matter called plasma. So an example of this is this one. So whenever deuterium or H3 and then the deuterium or H2 fused, so the end product will be helium, and then we also get a neutron. So from the word itself, fusion, when two light combines and then they form a heavier one. So that's what we call fusion. And then the second one is what we call the nuclear fission. So it's actually the inverse of fusion. So it is a reaction where the nucleus splits into two or more smaller nuclei. So the fusion from the light to heavy, and then the fission from the heavy to smaller nuclei. So this splits the atoms. So example, whenever a nucleus, so we have this one, is bombarded by neutron. So we've got a neutron there. So when you bombard a nucleus, so the end product will result to fission products. It's either neutrons. So there's a lot of neutrons, and there's also new nucleus since our nucleus will be split, and we'll be we will also discuss chain reaction. So actually chain reaction happens whenever there's a nuclear fission. So a chain reaction refers to a process in which neutrons released in fission produce an additional fission in at least one further nucleus. So in this example, so we have a neutron. So when we bombard a nucleus, so an example is uranium-235, our nucleus will split. And when nucleus split, that will emit lighter elements. So, and elements like the lighter nucleus, and then also neutrons. And then again, that neutrons will again bombard another nucleus, and then it will go through different stages. So that's what we call chain reaction. So we have first reaction, and then we have second reaction. And those chain reactions, it actually emits energy, and we'll discuss about that. So where does the energy released from nuclear reaction comes from? So the explanation for this is actually the Albert Einstein's theory of special relativity. which states that E equals mc squared. So the total mass of the fission products and emitted neutrons is found to be slightly less than the mass of the initial uranium nucleus. So at first, our nucleus have a bigger mass. And whenever a neutron bombards a nucleus, that results to a slightly less than mass of our original nucleus. So there's a mass that is missing, and that mass, the energy of that mass can be converted using this formula, which is E equals mc squared. I think this is very famous. So m, that's the mass, or the mass that we initially lost during the reaction, and then c is the speed of light squared. And when you multiply those quantities, we will get the energy. So that's actually basically the concept behind nuclear energy. So let's talk about the history of nuclear energy. So let's start in year 1895. So Wilhelm Röntgen discovers X-rays. And then in 1896, Henry Becquerel discovers rays emitted spontaneously from uranium salts. So these two, X-rays and these other rays, are actually comes from the nucleus. And in 1898, both the Curies identified two radioactive nuclides, polonium and radium, and they are the first one who termed the word radioactive. And in 1899, Ernest Rutherford distinguishes alpha and beta radiation and discovers half-life. In 1909, again, Rutherford discovers that most mass is concentrated in a small nucleus. So during this time, scientists still don't know the existence of nucleus or electrons, so they're still not sure. And then in 1920, again, theorizes neutrons. So in this year, they still don't know if either neutron actually exists. And then here's James Chadwick, and he's the first one to identify that there's really exists a neutrons inside atoms, and that's in year 1932. And then 1938, Otto Hahn, Franz Strassmann split uranium atoms with neutrons. So this is the first one. Scientists discover how to split neutrons. And then together with Lise Meitner and Otto Fritsch, name it fission. So this is the first, they're the first one who coined the term fission. That's in 1938. And then in 1942, Enrico Fermi achieves first nuclear chain reaction in Chicago, creating the first nuclear reactor, Chicago Pile 1 or CP1. 1945, so I think this one is very famous. So the world's first nuclear weapon test, the Trinity shot, is successful. So during this time, the bomb during World War II still not actually happened. So this is just the first test of nuclear weapon test. So maybe someone will ask, oh, why nuclear weapon tests also in this topic? So actually, nuclear weapon test, it uses nuclear energy. So that's how powerful nuclear energy is. So in August 1945, atomic bombs. So these two, very famous, the little boy and fat man dropped on Hiroshima and Nagasaki. 240,000 people died. So in this time, people know the power of nuclear energy. Year 1950, EBR-1 or the Experimental Breeder Reactor 1 reactor is the first to generate electricity in ARCO ID. So actually, after World War II, countries like the US and Russia, so they decided to stop the research and development of nuclear energy on war, but they actually decided to research on nuclear energy to produce electricity, and that is in year 1951. And in year 1954, USS Nautilus launches the first nuclear-powered submarine. So that's in the left photo. And then the right is the Obelisk reactor, which is in Russia. It's the first nuclear power plant to generate electricity for a grid. So yeah, so it's still for a grid, so it is not commercialized. And then in 1957, shipping port operates. So the first commercial. So the first one still not commercial, but they just applied it in electricity grid. And in 1957, that's the time shipping port is the first commercial nuclear power plant. So in year 1979, Three Mile Island reactor suffers a partial meltdown. So these are the most famous accidents. So first one is in 1975. So Three Mile Island is located in the US. Based on my research, there's no actual deaths. However, in 1986, Chernobyl, so this time, I think a lot of people died. So Chernobyl reactor suffers a large power excursion, resulting in the release of large amounts of radiation. So this is also caused by meltdown. So when you say meltdown, whenever nuclear energy cannot be controlled. So yeah, and in 2011, this time, the four reactors at Fukushima Daiichi suffer core meltdowns again, meltdowns. So it cannot, the energy was not controlled properly. So that's what happened. Hydrogen explosions. So radiation estimated to be 10% to 30% of Chernobyl. So Chernobyl is still the worst accident in nuclear energy. And then year 2013, Voyager 1 enters interstellar space after traveling the solar system for 36 years. It's powered by a plutonium-238 radioisotopic thermal generator. And actually, it is powered, this plutonium-238 is radioactive or radioisotopic, so it still uses nuclear energy. So we're done with the introduction. Let's go to the operation. So at first, get to know the most basic components of nuclear power plants. So first, the reactor. So the fuel, this one, the green one, heats pressurized water. So actually, fuel, that's where our uranium are located. So uranium or the radioactive components of our nuclear generator. Control rods or the gray absorb neutrons to control or terminate fission. So as I discussed before, there's a chain reaction during nuclear fission. So we need to control or maybe terminate that one because whenever you cannot control that one, meltdown will happen. And that's what happens to the three previous accidents. The second is the coolant and moderator. So this one. So fuel and control rods are surrounded by water. It serves as coolant. So that the energy, they call that the temperature will be as low as possible. And also it acts as a moderator. Third one is the steam generator. So hot water from the reactor is pumped through a heat exchanger, generate high pressure steam. So during uh, this part, that's where our steam was generated. It is generated through the hot water, which comes from our fuel, this one. So whenever our neutron bombarded these green fuels, that will generate a lot of heat, and that heat will go through this circuit, this red one, and then the temperature or the heat from these red circuit will go to this one. So this is another water right here, this blue one, and that will generate heat. So the heat will transfer from that one, and then that will finally generate our steam. So yeah, we've got the fourth part, which is the turbine generator. As we all know what generator does. So the steam drives electricity generator to produce electricity. So this is the part where the heat, which is a thermal energy, was converted to mechanical. That's the turbine, and then finally to electricity. And then we've got the condenser, which removes heat to convert steam back to water. So after the steam or the heat from the steam was used for the turbine, so that steam will be condensed so that the heat will be converted back to water. And then that water will be used again for the process. And then the sixth part is the cooling tower. So I think this is also can also see this in other nuclear power and I mean nuclear other power plants like coal. So cooling tower removes heat to return cooling water to near ambient temperature. So it also removes it just like a condenser. So yeah, actually there's a lot they call that there's many types of nuclear power plant. They were actually characterized in their nuclear reactor part. So the very famous one is the PWR or the pressurized water reactor. So in pressurized water reactor, we actually got two or three circuits. So first we have the first circuit, this one, the red one. So this actually directly connected to our fuel. So this one will generate the heat from our nuclear fission reactions. And then the heat will transfer to the second circuit, which is this blue circuit, this one. So the heat from this one will go to this second circuit, and then that will produce our steam. So, and then the steam will go to the turbine. And then once the turbine works, it will generate electricity. And then the heat from the turbine, the excessive heat will go to the condenser, and that condenser will remove the heat. And then we've got the last circuit here. This is the circuit used for the condenser to remove the heat from the turbine. Another most famous type is the boiling water reactor. So you can see the difference here. In the pressurized water reactor, the control rods and the fuels are not directly connected to the turbine. So you can see we've got first circuit, we got the second circuit. But in the boiling water reactor, we don't have first circuit or second circuit. So as you can see, it is directly connected to the turbine. So once the heat was produced through the nuclear fission, the heat will go directly to the turbine, and then the turbine will generate heat. So compared to the pressurized water, boiling water reactor is directly connected to the control rods. So the process is faster compared to pressurized water. And then let's look. So this is actually what you see inside the green fuel. So this one, there's rod, and this the green one. So this is the fuel rod. So that contains pellets. So these are uraniums. So uraniums are stuck inside. So and then whenever neutron is bombarded, so they create a chain reaction. So so these are the concrete shields. So this is to protect again from the heat. And yeah, we've got movable control rod. So this is to minimize uh wait to minimize the production of nucleus from the reaction. So both the control rod and the coolant, this one, uh, the water, they are both used to control our nuclear fission. So there's actually other types of nuclear reactors. The main two types are the thermal reactor and the fast breeder reactor. So from the word thermal, reactor types that rely on fission due to slow neutrons. So as I've discussed before, we've got control rod and water as moderator. So those two control our neutrons so that we will have slow neutrons. So hence uses moderators, just like water, are called thermal reactors. So thermal reactors just means we uses slow neutrons. And if it got three subtypes. So first is the light water moderator. So uses ordinary water as both coolant and moderator. So what I've discussed, the two Previously, the PWR and BWR, they are considered light water moderator because they both uses ordinary water only as both coolant for the temperature and moderator for slowing the nutrients. Other subtype is the heavy water moderator. So from the word itself, heavy water, instead of using ordinary water, it actually uses heavy water. So as its colon moderator. So the most common type for this one is CANDU or the Canada deuterium uranium. So deuterium is the term for the heavy water. And lastly, we've got the graphite moderated. So there are actually two types, the gas cooled reactors, a special class of reactors that uses gas such as carbon dioxide or helium as coolant. So as we all know, the pressurized water and boiling water uses ordinary water as coolant, but in gas cooled, it uses carbon dioxide. And then the second subpart is the light water cooled graphite moderated reactor or the LWGR uses ordinary water as coolant and graphite as moderator. So it is also known as high powered channel type reactor. So these two uses graphite as moderator, thus they are part of the graphite moderated. And then lastly, we have the fast breeder reactor. So previously, I've said that thermal reactor uses slow neutrons. So the other hand, fast breeder is the opposite. So in contrast, fast breeder reactor or FBR uses fast neutrons to cause fission in the fuel. Hence, a moderator is not needed. So note that moderator is not needed. So we don't need ordinary water or heavy water to moderate our neutrons because it can function even using fast neutrons. So also the word breeder comes from this. So when the amount of new fuel produced is larger than the amount of fuel consumed, the reactor is said to be capable of breeding. So yeah, when we produce more compared to what we use, that can be considered as breeding. And let's talk about the nuclear fuel cycle. So there's actually two parts, the front end and the back end. So for the front end, first one is the uranium mining. So I think almost the same with other power plants. The first part is always mining. So over 70% of uranium production is achieved by the extraction of ore using conventional open pit or underground mining methods. Then once uranium mining is done, we'll go to uranium milling. So milling is the process through which mined uranium ore is physically reduced to a suitable size, then extract and purify uranium. So the product of milling is known as yellow cake, U3O8. So this is an example of the yellow cake. And then the third process is the conversion. So conversion is the chemical process that transforms yellow cake into uranium hexafluoride. So uranium hexafluoride is solid at room temperature, but readily turns into gas at temperature below the boiling point of water. So why do we need to convert? Because naturally, the the most abundant uranium isotope is uranium 238, but we need uranium 235 for the nuclear power plant. So that's why we need to convert it to yellow cake and then to hexafluoride or gas because at gas we can split the uranium 238 and U35 effectively. And we've got the enrichment. So this is what I said before. So enrichment involves the partial separation. So once we've converted the yellow cake to the gas, we can separate it now, the two isotopes. So U35 and U238. So actually we use 235, but U38 is more abundant. That's why we need to separate the two. And then the fuel fabrication. So this is what we call the fuel pellets. I've shown before. This is what inside the fuel, inside the nuclear reactor. So fuel production involves the transformation of UF6 into uranium dioxide powder. So after being turned to gas, it will now be turned to powder, which is then pressed and heated at high temperatures up to 1400 degrees Celsius to produce die-sized cylindrical pellets. So this one. So the die-sized cylindrical pellets are what inside the fuel. And then after the front end, let's go to the back end. What happens after fuels are processed? So there's actually two main main methods or process. Ones are nuclear fuel was used. So first is reprocessing. So reprocessing is the operation by which the unused energy content of spent fuel is recovered with an intention of future reuse, or in some cases to condition the fuel for disposal. So yeah, so in figure 3.2, you can see that spent fuel, 1% of that is plutonium and 96% is uranium. Other 3% is high level waste. And this 96% spent fuel can be used for reprocessing. So part of it can be recovered. So you can see, so once recovered, it can be used again. And then some can be recycled also and vitrified. So this term vitrified just means that the high level waste will be torn to a somewhat crystallized nature because it can be more safe. It is safer that way when you vitrified high level waste once you dispose spent fuels. Then the second process is the decommissioning. So actually decommissioning is when the power plant life ends. So there's actually a lot of process, but the first one is the close out. So the spent fuel is recovered from the reactor and stored in the usual way. So the liquid systems are drained, the operating systems are disconnected, and external apertures in the plant blocked or sealed. So this is what happens when a power plant closes. And then once closed out, we'll go to the decontamination and dismantling. So all surfaces are washed with water or treated by mechanical, chemical, or electrochemical means to remove radioactivity or decontamination. So this is very important, especially the waste of nuclear power plants are very radioactive in nature. And then we also the demolition and site clearance. So unless parts of the remaining facilities are to be used for some other purposes, all the plant and materials are removed and the site delicensed and made available for new uses. So yeah, so whenever useless parts, so you need to demolish and so that the site can be used again for another one. And lastly, decommissioning waste. So the European Commission estimates that decommissioning of an average nuclear power plant produces up to 10,000 cubic meter of radioactive waste. So these are example of the waste from the nuclear power plant. So yeah, so this is the summarization of the nuclear fuel cycle. So first, mining, uranium mining and milling, and then turning it to yellow cake. Then conversion to gas, and then enrichment. So enrichment, we need to have more U35 compared to U38. And then fuel fabrication, and then yeah, after that we can produce electricity, and then after that we've got spent fuel, which will be go to either processing or to waste disposal. So the nature of loads. So I've researched about nuclear energy, and they're dominantly or almost they are used as base load supply. So here, so I think Sir Renel discussed this a while ago. So base load nuclear power is used for base load because it has very steady output, as you can see right here. So yeah, it has a very big capacity factor, which will be discussed later. So that's why nuclear power is mainly used as base load supply. And let's go to the third topic, the status. So first, let's go to the global status. So in 2023, nuclear power plants supplied 2,602 terawatt hour of electricity, up from 2,545 terawatts per hour in 2022. So 2,602 terawatts is when you compare it to other energy sources, it's approximately 4% of the total energy. And these are from the each region. So in 2022, nuclear generation increased by 37 terawatts per hour in Asia. So this is mostly because of China, also Japan and India and Korea. And on the other hand, the output declined by 22 terawatts per hour in East Europe and Russia. So this is mostly because of the war in Ukraine and Russia. East Europe, which also Ukraine is part of, has a lot of nuclear power plant. And when the war happened, so some of the power plants was closed. So that's why there's some decline in the total power output from this region. And then in the West and Central Europe, there's also a decline by 112 terawatts per hour. So this is mostly because of Germany. So Germany actually closes all their nuclear power plants recently, if I'm not mistaken, in 2023. So that's the biggest cause of this decline. And then in North America, six terawatts per hour decline. So North America, just mostly from the US. And then lastly, minor decreases in South America and in Africa. So in Africa, if I'm not mistaken, the only nation having nuclear power plant is South Africa. And then in South America, the only two nations are the Brazil and Argentina. So we got this graph. So you can see the green part is the West and Central Europe. So together with North America, the blue one, they comprised the biggest percentage from the output of nuclear power plants. And then we also have Asia here, the light blue. And we've got small part from the East Europe and Russia, the orange one. And South America, this one, the red one. South America and Africa has the lowest output. So you can see the trend from 2012 to 2022, mostly our output averages in 2,500 terawatts per hour. And we also have this line graph to show the trends. So first, West and Central Europe, as I've discussed, there's a decline. This is mostly because Germany closes their all power plants. North America, slight decline. Uh, and then let's focus on Asia. This one, light blue. So as you can see, there's a big steep from 2010 to 2012. If you if you're curious about that, that is because that's the time Fukushima disaster happened. So that time is around 2011. So during this time, a lot of nuclear power plants from Japan was closed. So that's why there's a big steep right there from 2010 to 2012. And then the other regions, more like more stable right there. A very low output from both the South America and from the Africa. And then there's the capacity factors. So I discussed before that nuclear energy was mainly used as a base load because it has a very high capacity factors. So let's look at the trends. So in 1970s, above 90% capacity factor, dark blue only constitute a small part of the entire nuclear power plants. But during 2010 up to 2022, capacity factor almost half, as you can see there, almost 90%, and then 80 to 90%, the light blue, they're the largest. They have the largest part in the capacity factor. So meaning, nuclear power plants are very high. It's very efficient and very effective in turning uranium to nuclear power because they have a very big capacity factor. There's a lot of more than 90% and then 80 to 90%. And the 0 to 40% is very small compared to the big ones. Then let's look at the other types of nuclear reactors. So the total number of operable reactors at year end 2022 was 437, up one from 2021. So just over 70% of all operable reactors are pressurized water reactors. So as I've said before, the most common reactor is the PWR or the pressurized water reactor. So as you can see, the total of PWR is around 307. Compared it to the others are very minimal, and PWR is very famous, 307. And from the total of 307, most of that came from Asia, 104, from North America, 61, and then from West and Central Europe, 98. And then the second most famous, as you can see here, is the BWR, or the boiling water reactor. So these two, the BWR and PWR, as I said before, is part of the light water part because they uses ordinary waters, both their coolant and their moderator. So GCR, so this is the gas cooled. So pressurized high water, also famous with 47 of total. And then mostly still coming from the Asia and then from the North America. So local status. So let's look at the status of the nuclear power plant in the Philippines. So these are the key points in the history of the Philippines' nuclear energy ambition. So first in 1958, the first president, Carlos P. Garcia, was the first one to consider utilizing nuclear energy. And then he created the Philippine Atomic Energy Commission, or the PAEC. And then the next one in 1960, still, he created the first nuclear reactor for research in 1960. 1973, we got Ferdinand E. Marcos. So announced in 1973 that a nuclear power plant will be built to reduce the country's dependence on imported oil. So during this time, 1970s, this time the world has oil crisis. So the world really needs energy, a lot of energy, but the oil is very limited. So that's why former Ferdinand E. Marcos Sr., he saw the potential of nuclear energy and nuclear power plant. That's in 1973. And in 1976, so they started the construction. So this is very famous. If I'm not mistaken, this is the only nuclear power plant in the Philippines, which is the BNPP, or the Bataan Nuclear Power Plant. So they started the construction 1976. So Westinghouse Electric at the contract of 500 million US dollars. So and in 1979, however, unfortunately, the Three Mile Island accident happened. So so the Philippines, they're still questioning whether a nuclear power plant is safe because just 3 years after the construction of the Bataan nuclear power plant, the Three Mile Island accident happens. But in 1996, yeah, in 1996, actually, this part, Bataan was already constructed. However, people power revolution and the Chernobyl disaster occurred. So in the former Soviet Union, and the administration of former President Corazon Aquino decided not to operate. So this is mainly because of the Chernobyl disaster, which caused a lot of death. So again, unfortunately, there's an accident happened, so that's why the Bataan was not operated even if it's already done construction. And in 2008, so former President Gloria sought for a mission review by IEA and commissioned the Korea Electric Power Corporation to conduct a feasibility study. So once again, they opened the possibility of having a nuclear power plant. And Korea this time is they're actually they have a lot of power plants this time. So Korea is very successful in nuclear power plants. So that's why they commissioned the GEPCO. And then the following years, 2011, however, again, the Fukushima incident happened. So which sparked renewed fears. So this the third time it happens, right? So again, the people from the Philippines is afraid of nuclear power plant because of these incidents. So nevertheless, the inclusion of nuclear energy in the power mix remained. So again, the Republic of the Philippines is still hoping to use nuclear energy in the future. And in 2006, Duterte administration expressed interest in nuclear energy, and the DOE reached out to the IEA for review missions on the prospect of developing a nuclear energy program. And presently, we got Ferdinand Marcos Jr. So in his Philippine Development Plan of 2023 to 2028 articulates, so there's actually three. First, the government will explore the inclusion of nuclear energy, the power generation mix. So the Philippines still very hoping to use nuclear energy. And then second, any decision by the government to allow investment in nuclear power plants will have to be backed by rigorous scientific studies that are consistent with IEA guidelines. So we'll discuss this later. Just a summary of IAEA guidelines. And lastly, the legal and regulatory framework for nuclear energy will be crafted. So here is the nuclear power infrastructure development. So this is the framework which the country wants to construct new power plants. So they need to follow this one. So at first we have the phase one. This is the pre-project activities. So considerations before a decision to launch a nuclear power program is taken. So there's a lot of consideration, the safety, the radioactive waste, and of course the people and the economy, of course, if the project will have a positive income. So milestone one, ready to make an eligible commitment to a nuclear power program. So after considering a lot of decisions and factors, we will get to milestone one. We're ready to commit to have nuclear power program. And then second is the project development, the phase two. In this part, so the preparatory work for the contracting and construction of the nuclear power plant after a policy decision has been taken years. And the milestone of that, once the contract is done, we are ready to invite bids or negotiate a contract for the first nuclear power plant. After that one is the phase three. Once we have the contract for our nuclear power plant, we have the final investment decision, contracting, and the construction. So phase three activities to implement the first nuclear power plant. Then after that, we have the milestone three. And then we're ready to commission and operate the first nuclear power plant. After that, I've discussed this a while ago. After the commissioning operation, we'll go to the decommissioning or the closing of our nuclear power plant. And lastly, I will talk about the future of nuclear energy. So I've decided to talk about the advantages and disadvantages because this will help on the future whether the people will still like Filipino citizen will like nuclear energy in the future. So why nuclear power is attractive? So it's actually four. So first one, nuclear power is among the safest sources of electricity. So don't get me wrong, the safest because when it comes to the health effects, so you can see here, nuclear, the deaths from air pollution and accident, nuclear is the smallest, as you can see, compared to coal. around 1,000, so 30 deaths per 1,000 grams. So we can say, at, in terms of deaths from pollution, nuclear is the safest one compared to others. So that's why it's very attractive. Second one is that nuclear power helps combat climate change. So again, this is connected to the first one, wherein the emission of nuclear power plants is very limited compared to other power plants. That's why it's really help for the climate change. And we can consider nuclear power plants as clean energy because it emits very low, if not zero emission, gas emission. The third one, most reliable energy source. So we can see most reliable because it has a very high effect. It is very efficient when it comes to the power output, and also it is very stable. So so we've got a graph before for the capacity factor. Almost half of the capacity factor of the nuclear power plants are over 90%. That is very big compared to other. So as you can see here, 92% nuclear power plant. So it's very effective compared to others. Compared to coal, which is only 54%, the natural gas 55, and the solar and wind both below 40%. And lastly, nuclear fuel is extremely energy dense. So because one uranium fuel pellet that's very small, size of a pencil eraser, imagine that, provides as much energy as 1 ton of coal, 149 gallons of oil, and a 17,000 cubic feet of natural gas. So imagine the power of nuclear energy. However, there are risks. That's why nuclear energy is still in doubt for the Filipino. So the first one, nuclear accidents. So I guess this is the most common, the biggest problem for the Filipino citizens, why they don't like nuclear energy because of nuclear accidents. Because our radioactive materials in the plume from the nuclear power plant can settle and contaminate people who are outdoors, buildings, food, water, and livestock. And imagine when there's an accident, nuclear accident, you can see radioactive waste or radioactive materials. However, you don't know that you're already contaminated by it. And one of it is your cell dam. You can see in the left, we've got the cell damaged by radiation. And sometimes it can be repaired. However, if that damage is not repaired, so that will cause cancer. That's why many people disagree with having nuclear energy because of this one. Because whenever you have damaged cell, it's possible to have a cancer or a partial loss of cell functions or a possible genetic effects. And then we've got the second one, radioactive waste. So hazardous because contains or emits radioactive particles, which if not properly managed can be a risk to human health and environment. So also the problem with radioactive waste, the waste are radioactive for almost very long years, 1,000 years. That's why having a safe radioactive waste system is very important and to properly manage them. And the last one is, this one is the weapon of mass destruction. So these are the nuclear bomb, and we also have hydrogen bomb. So a weapon of mass destruction is a nuclear, radiological, chemical, biological, or other device that is intended to harm a large number of people. So the discovery of nuclear energy also caused the discovery of weapon of mass destruction. These are the nuclear bombs and hydrogen bombs. So and let's talk about the future and the emerging technologies. So there's actually four generations of nuclear reactors. So the first prototypes. So an example of shipping port. So during this period, France developed a reactor technology using natural uranium for the fuel since it did not have access to uranium enrichment technologies. So during this time, they're still using natural uranium, which is U-238. It's still not able to separate U-235 from U-238. Generation 2, or the commercial production of electricity. So Gen 2 represents mainly operated reactors in France, Russia, and other European countries, Japan, and USA. So the lifetime extension from 30 to 40 years to 50 to 60 years. So the three accidents happened in Three Mile Island, Chernobyl, and Fukushima. They're actually part of the Generation 2 reactors. Generation 3, so these are the nuclear reactors. The improvements in the areas of fuel technology, thermal efficiency, modularized construction, safety systems, especially the use of passive rather than active systems, and standardized design. So these generation are still in construction. So take note of this one, use of passive rather than active systems. So these systems don't need human to manually operate. That's why they are more safer because they only need passive systems compared to active ones. And then lastly, these are the future or the generation 4. So the fourth generation refers to reactors currently in design phase, which could be deployed on the industrial scale by around 2050. So their design incorporates a number of technological breakthroughs with respect to what has been built so far. So let's take a closer look. So why choose the fast reactor technology? So as you can see, example of the generation 4, the gas-cooled fast reactor, the lead-cooled fast reactor. We also have sodium-cooled fast reactor. So these are all called fast reactor. So why fast reactors? So fast reactors can burn all of the natural uranium, including depleted uranium, whereas today's reactors only burn less than 1%. So as I discussed before, the most common now is the thermal reactors, which uses slow neutrons. So the development is going to the fast reactors, wherein it don't need any moderator to slow our neutrons because fast reactor can use fast neutrons. And then, so why choose sodium or helium? So others here, helium does not become radioactive upon exposure to neutron radiation. So compared to ordinary water, helium is safer in terms of radioactive. And then sodium has high thermal conductivity and high heat capacity. So compared to water, sodium is can be used to control temperature compared to the water. So that's why the research and development is focusing on these two as part of the coolant. And then we also have small modular reactors or the SMR. So this is an example. So we already discussed this types, the pressurized, reactor coolant, steam generator, control rods, and core. So as you can see, it is very small compared to the total nuclear power plant I've discussed before. So this is in development. So instead of going big, scientists and engineers went small, developing many reactors. So this is very actually true to all, in industrial. So we'll know at first computers are very big and now they're somewhat very small or smaller. So that's also the plan for nuclear power plants. They want to go small. So there's actually four benefits. So first, less preparation. Second, ideal for locations that cannot support large reactors. So I think this is very important because being small, you don't need a large area of land. Third, flexibility. Flexibility because you can move it compared to the big reactors. And lastly, new business. So having this one, new businesses, scientists and workers can have new work when constructing SMR. So we've got new businesses. And lastly, we've got micro reactors. So this is much smaller to SMR. So microreactor designs vary, but most would be able to produce. So this is just an example of the future. So wherein microreactors can be put inside the truck. So that's why they can move freely. So the benefits is that seamless integration with renewable within microgrids can be used for emergency response. So this is very important since our nuclear energy, the source of our nuclear energy can be moved freely because it is within truck or vehicle. So a longer core life, operating for up to 10 years without refueling. And lastly, can be quickly removed from sites and exchanged for new ones. So these are my references. So that's all, ma'am. Thank you.